So this starts our chapter 5. Chapter 5 is all about probability. And when we think about probability, there's really 3 types. We've got relative frequency. So we call that empirical probability. It's experimental. So like the number of times an event occurs during experimental trials. So if you're flipping a coin 10 times and the outcome, it lands on heads 4 times and tails 6 times, that's your experimental relative empirical probability. On the other side of that, we've got theoretical probability. So when we talk about theoretical probability, we're talking about probability based on reasoning. So I'm thinking about what it would look like if I flip a coin. And there's 2 equally possible outcomes. So there's a 50% chance that it lands on heads, a 50% chance that it lands on tails. So if I flip the coin 10 times, I expect it to land on heads 5 times and tails 5 times. Now we know that in practice that doesn't always happen, so that's why the 2 probabilities are different. We have a third type of probability that's called personal or subjective probability. And it's based on our own personal experiences. So, let's say that in your experience, after 2 days of rain, there's always a day of sunshine. So that's based on your own experience. It's not necessarily grounded in any theory or experiment. It's just based on your own general opinion and your observations. That's what you think. So that's personal probability or subjective. So when we talk about these types of probabilities, we want to be able to describe them. And 2 important ways to describe our outcomes are as mutually exclusive or independent. And these are different. When we talk about things being mutually exclusive, we think about them being disjoint. So they can't both happen at the same time. So if we were to draw a Venn diagram, mutually exclusive events would have their own circles. There would be no overlap. So that coin's either going to land on heads or it's going to land on tails. There's no in between, there's no mixture. That's just the 2 possible outcomes. The other type is independent. So one outcome doesn't affect the other outcome. So if I draw a card out of a deck and it's the 2 of hearts, and then I flip a coin and it lands on heads, those 2 things are independent. Drawing the card out of the deck does not determine what side the coin's going to land on. So 2 different ways to look at the outcomes of those 2 different cases. So outcomes are just the results We also want to make sure we know what it means to have a law of large numbers. So that just means that the more times you do an experiment or the more repetitions that you have, the closer your relative frequency is going to come to that theoretical probability. So if I flip a coin 10 times, it might be close to 50% or might not. If I flip a coin 1,000 times or 10,000 times, it's going to get closer and closer to that 50%. It may not be perfect, but it's going to get close. Our experiment is anything that we repeat to find out what the outcome is, And our sample space is all of the possible outcomes. So we usually denote sample space as a capital S in parentheses. So just some vocabulary that we have to know before we can talk about some specific cases. So we represent the probability with a capital P. So if I want to find the probability of any particular event, we could say the probability of, and instead of that E being there, we could write the probability of landing on tails. So we could write P of T. Or we could write the probability of landing on heads. So we could write P, and in parentheses, we could write heads. And that gives us the probability of whatever an event is. Now remember, probability has to be somewhere between 0 and 1. It can be equal to 0. It might be impossible. It might not ever happen. And it might be 1. It might be guaranteed to happen. But those are the only values, somewhere between 0 and 1. And the sum of all of our outcomes has to be 1. So we can't go over 100% basically. Probability of landing on tails, 0.5, 50% of the time if we want a percentage. Probability of landing on tails, 0.5, 50% of the time if we want a percentage. And if we add those two together, it's 1. There's nothing else that's going to happen in that scenario. So let's look at remember our theoretical probability we can write as a ratio. So if we want to find the probability of a certain event happening, we have the number of times that that event happens over the total number of trials. And it's important to remember in statistics, we're going to change up the rules just a little bit. So usually when you see the word and in a math problem, you think add. I have 5 oranges and you have 5 oranges. How many do we have in all? 10. We usually add together. But in statistics, we switch it, or signals addition and signals multiplication. So think about probability of disjoint events. If I want to find the probability that one thing or the other thing happens, as long as those are disjoint, I can just add those two together. The probability of rolling a 2 or a 3 on a fair 6-sided die. Well, the probability of rolling a 2 is 1 out of 6. There's 1, 2, so there's 1 possibility of landing on a 2. There are 6 possible outcomes. So the probability of rolling a 2 is 1 out of 6. The probability of rolling a 3 is also 1 out of 6. So those two things can't happen at the same time. Those are disjoint events. So the probability of rolling a 2 or a 3, or means I add 1/6 plus 1/6. That's 2/6 or a third. So I have a 1 in 3 chance of rolling a 2 or a 3. I have a 33% chance if we want to change it into a percentage. What if I changed it up? What if we're not looking for a specific number? What if I want the probability that I land on an even or an odd number when I roll that die? Well, even number, if I'm talking about a 6-sided die, even numbers are 2, 4, and 6. So there are 3 possible even numbers that we could land on out of all 6 sides. And an odd number, 1, 3, and 5, there are 3 possibilities there out of 6 possible outcomes. So the probability of landing on an even or an odd number is 6 out of 6 or 1. We are guaranteed to land on one of those two things. So that's what the addition rule for disjoint events looks like. Now, sometimes we're going to deal with things that have an overlap. So what if we're talking about this general addition rule? So we're not making the requirement that it has to be disjoint. It's just anything. This would work for any case. We have to subtract the overlapped part because we've counted it in this event and we've counted it in this event, and it's been doubled up basically. So what if, using that same setup with our six-sided die, what if we're looking for the probability of rolling a 2 or an even number? 2 or even. Well, rolling a 2 is just 2. So that's a 1 out of 6 case. 1 out of 6 chances that we're going to roll a 2. That's the same for any number, but in this case specifically a 2. Rolling an even number on a die would happen if we roll a 2, a 4, or a 6. Now, notice I wrote down 2 for both of these. I've counted the 2 in this set, and I've counted the 2 in this set. So that's going to make it unfair because I've counted it twice. So we've got a 1 out of 6 chance for a 2. We've got a 3 out of 6 chance for an even. But since I counted that 2, in both cases, we have to subtract the overlapped part. So that 2 happened in both. We have one outcome that happened in both of our events, so we have to subtract it out. That means 1/6 plus 3/6 minus 1/6 gives us 3 out of 6, or 1/2. Because this is where overlap happened. We counted that 2. We had one outcome that happened in both events, so I had to subtract it. Because really, the probability of rolling an even number and the probability of rolling a 2 or an even number is the same because 2 is included in that set of even outcomes. Now, something that's really handy is a probability model when we list all of the possible outcomes of an event. And this is what that looks like. So you've probably seen this before. A lot of times we look at it with like creating an outfit. You have 3 shirts and 4 pairs of pants and they all match. And we want to figure out how many outfits we can make out of those 3 shirts and 4 pairs of pants. So we would list all of them out. So let's say that we're going to flip the coin twice. The first outcome could be heads or tails. Those are my only options. The second outcome, after I flip the heads once, I could land on heads again, or it could switch and be tails. After I've landed on tails once, it could switch and be heads, or it could land on tails again. So all of my possible outcomes are both heads, heads then tails, tails then heads, and then both tails. So we've got all of those possible outcomes. Those are the only way that it could be. So when we're talking about a probability model, it helps us to organize all of that information and put it in the right order. So let's move on. We've talked about the addition rule and the general addition rule. Let's add some more rules on here. So the complement rule just means that the probability of an event occurring and the probability of it not occurring has to be equal to 1. Either it happens or it doesn't. So the complement just means that we're finding the piece that is missing from it adding up to 1. So the probability that any event happens is 1 minus the probability that it doesn't. So this means the probability it doesn't happen. And this is the probability that it does happen. So if we add those two together, either it happens or not. That has to add up to 1. We can shift that around. We can trade places here, basically add the not happen to this side and subtract that it happens to the other side and switch that equation around. So the probability that something doesn't happen is equal to 1 minus the probability that it does. So that's just called the complement rule. It has to add up to 1. And that little C superscript just means complement. So probability of the event, probability of the complement of the event. So moving on, adding a little bit to this, we have a multiplication rule. So we said that or means addition, and means multiplication. So going back to that, probability model, what if I wanted to find the probability that we land on heads and we land on heads again? So what's the probability that that order happens? Heads and heads. So here I can see that out of my 4 outcomes, it happens once. So really I have a 1 in 4 chance. 25% chance, right? So let's work this out. The probability that I land on heads the first time is a 1 in 2 chance. And the probability that I land on heads the second time is a 1 in 2 chance. So it's a 1 in 4 possibility, or a 25% chance. So we can see it in the probability model that it's going to be 1 in 4, and we can see it in this multiplication rule that it's going to be 1 in 4. Now this only works for independent events. We have to include an extra step if they're not independent. But let's look at a different type of example. So let's say that you're going to take your car to be inspected and your friend's going to take their car to be inspected. They're completely independent. My car passing doesn't determine if your car is going to pass or fail whenever you go after I do. So we've got 2 cars, they're independent. There's a 75% chance that a car passes inspection based on this case. So the probability that the car passes is 75%. The probability that it doesn't pass is 25%. So those are complements. They have to add up to 1. So pass is 75%, doesn't pass is 25%. That adds up. So what if I want to find the probability that both of our cars pass, or your car and your friend's car pass? So I want to find the probability of a pass and a pass. Well, based on this multiplication rule, I take the probability that it passes and multiply by the probability that mine passes. So it's going to look like this. 0.75 times 0.75. So the probability that both of us pass is going to be 56.25% if we want to change that into a percentage. Now make sure if you're doing the probability as a decimal that you leave it this way. If you want to write it as a percent, that's fine. If you think about it that way, just make sure that you put your decimal in the correct spot and that you put that percent sign on the end so that you can differentiate between the probability as a decimal and the probability as a percentage. Okay, this one's a little bit tougher. the probability that at least one car passes. The probability that at least one car passes. So think about that just a second. See what you think about how that's going to turn out. Probability that at least one car passes. So there are a couple ways we can look at this. I'm going to try to cover up my work here. So we could have your car could pass, your friend's car could fail. Well, and your friend's car could pass or fail. So our possible outcomes look kind of like the toss in the coin problem. We could have both pass, you pass and your friend fails, you fail and your friend passes, or you both fail. So this says at least one car passes. So we could both pass, you could, or your friend could. All of those satisfy at least one. The only case where this doesn't work is if you both fail. So that's the only one that this doesn't include. So if we wanted to, we could do 1 minus the probability that we both fail. And that's what this first example is. So 1 minus the probability that we both fail. The probability of failure is 25% or 0.25. So 1 minus 0.25 times 0.25 gives us a 93.75% chance that at least one of us passes. There's one more way we could look at this. We could look at it as the probability that I pass or the probability that you pass minus that overlap, the probability that we both pass. And it gives us that same outcome. It works both ways. So more than one way to look at those at least problems. Well, why don't you try a couple of these? These are kind of like the ones we've been working on. The first one says, consider rolling a 6-sided die and tossing a coin. Write down the sample space. So sample space means all of the possible outcomes. What could possibly happen when you roll a 6-sided die? Pair that with all of the possibilities of what could possibly happen when you toss a fair 2-sided coin. Once you have that written down, you can use it to help you answer the next two. What is the probability of rolling an even number and tossing a heads? Write down the success from the sample space. So and means both things have to happen. You don't even have to use a formula for this one because you have the sample space written down. And since everything's fair and equally likely, we don't have to use any special formulas. So let's look at this first one. Our possible outcomes for rolling a 6-sided die would be 1, 2, 3, 4, 5, and 6. So those are our possible outcomes. We could roll any of those numbers, and the outcome for tossing a coin could be heads. So we might roll a 1 and land on heads, roll a 2 and land on heads, and so on. The other possibility is that we could land on any of those numbers, and then the coin could land on tails. So we have 12 total possible outcomes for rolling a 6-sided die and tossing a coin at the same time. 12 possible outcomes. Those are the only things that could possibly happen. Based on what we know about rolling a coin or rolling a die and tossing a coin, there's not going to be any other surprises. It's not going to be on the edge or anything like that. Not for a fair coin and a fair die. So for the second one, it said we were looking for the probability that we roll an even number and it lands on heads. So the possibilities here, even number, 2, 4, or 6, and it lands on heads. So 3 out of the 12 possibilities satisfy that requirement. So it would be 1/4. Now we can do this by using the formula, the probability of even and landing on heads. So the probability that we roll an even number on a die would be 3 out of 6. And the probability that we land on heads when we flip a coin would be 1 out of 2. And if we multiply straight across, we get 3 out of 12, which simplifies to that same 1/4. So we can do it if we have the sample space written down and we can just circle it and say this is how many times that particular thing happens out of the total number of outcomes. We can also do it if we know the probabilities of each one of those disjoint events, and we can use the formula. So let's look at that last one. The probability of rolling an even number or tossing a heads. So heads, let's switch up. Heads would be any of these. Possible outcomes. Even number, so 2, 4, and 6. 2, 4, and 6. So if we want to count the number of outcomes that apply, we've got 6, 7, 8, 9 out of 12 possible outcomes give us an even number or heads. So that would give us 3/4. Now, the probability of even or heads, notice that if both of those things happened, I counted it in both sets. So these 3 things happened twice. That means these are not disjoint events. There's an overlap. So if I'm going to use the formula, we have to find the probability that we land on even. So that's 3 out of 6 plus the probability that we land on heads. That's 1 out of 2. Minus the intersection. Now, we could have counted this based on these up here. We could have used for even, we could have used 6 out of 12. For heads, we could have used 6 out of 12. But then there's an intersection, these 3 out of 12 outcomes that overlaps. So if we work this out using our fractions, we're still going to end up with 9/12 or 3/4. So it doesn't matter if you use the sample space or if you use the formulas. Now the sample space is great, really is the easier of the two. I like to be able to see all the outcomes, but sometimes you have too many in your sample space for that to be effective. So it would take forever to write down 150 or 350 different possible outcomes and then to go through and circle all of the ones that satisfy whatever it is that your outcome's supposed to be, your probability of a success. So eventually, it really makes sense if we switch over and use the formulas, but being able to do both helps us see where those numbers come from. So let's look at another one. What if instead of just using rolling a die and tossing a coin, we're talking about picking a card out of a deck? So it's important that we know all of the attributes of a deck before we start trying to do problems that involve all of this. So there are 4 different suits: diamonds, hearts, spades, and clubs. Diamonds and hearts are red, spades and clubs are black, so half are black and half are red. Each suit has 13 different cards. And a deck of cards has 52 cards. And if we're talking about a face card, we're talking about a jack, queen, or king, the ones that actually have faces on them. So keeping all of that in mind, think about the probability of selecting a red queen. Would we want to write that probability as finding a red and a queen? Or would we want it to be the probability of red or a queen? Does that need to be an and, or does it need to be an or? Well, the probability of selecting a red queen, if we wrote out all of the sample space, there's a queen of diamonds and a queen of hearts. There are 2 possible red queens in a deck. So if I wanted to represent this with a probability, I would want to write it as red and a queen. I want both of those things to happen. If we said red or a queen, it could be any of the red cards or any of the queen cards. So it could be the queen of hearts, the queen of diamonds, the queen of spades, or the queen of clubs, and it could be any of those other red cards. And remember, red cards are half of the deck. So that would drastically change my probability if I wrote it incorrectly. So if I wanted the probability of a red queen, we would use and. So let's find the probability of selecting a red queen. And we just did that, but we will write it down. So if we're finding the probability of red and a queen, we could have the queen of hearts or the queen of diamonds. That's 2 possible outcomes out of the whole deck. There are 2 red queens in the deck, so 1 out of 52. Or if we simplify it, 2 out of 52, and if we simplify it, 1 out of 26. So let's switch and do the other one. Let's find the probability of finding a red or a queen. So remember, or means that we add. We could look at this whole list of cards up here and count it out. or we could use the formula. And at this point, instead of listing out 52 different cards and selecting the ones that are reds or queens and writing down that number, it's going to be more, it's going to make more sense if we just use the formula. So red cards, there are 26 out of 52. Half of them are red, half of them are black. Plus, there are 4 queens in the deck, one of each suit. Now the problem is we have an intersection here. 2 of those red cards are also queens. We counted these 2 twice. So we have to subtract that overlapped part from my answer, or it's not going to be accurate. We've counted 2 queens in the red cards and 2 red cards in the queens. So it happened in both places. We've got to take out that overlapped portion. So if we do these calculations, since we've got our common denominators here, 26 plus 4 minus 2 gives me 28 out of 52. Or if we simplify it, 7 out of 13. We could change all of these into percentages if we wanted to. But we don't have to. Ratios are fine. Okay. So we have lots of different scenarios that we could look at when we talk about probabilities and when we're talking about 2 different events and the intersections of events. One good way to organize these is with a contingency table. Now, we've already talked about contingency table as a way to organize information. So let's look at this example. So notice I have this contingency table. This is based on the gender of the people who are participating in this Pick Your Prize promotion and the prize that they chose. Now, obviously, this one's a little dated, but it'll work. So we've got men and women. We've got MP3 players, cameras, and bicycles. So these are our possible outcomes. And notice that our marginal totals are here too. So remember, marginal totals are the ones that are on the outside. It's what happens if we add up our rows and columns. Now, we had a total of 478 people who participated in this promotion. Of those 478 people, we had 227 men and 251 women. If we add those 2 totals together, we'll get the grand total for the whole promotion. Of the prizes that were selected, we had a total of 247 MP3 players, 141 cameras, and 90 bicycles. If we add all of those totals together, we also come to 478. So we have lots of information in this one table, this one contingency table. If I wanted to find the probability that a random person who participated in the promotion was a woman, that would be a marginal probability. I don't have to know anything about any of these 3 columns, the types of prizes that they chose. I just want to know how many of the people who participated were women. So if I look at that value, I'm looking at the total number of women over the total number of participants, and that gives me a probability. So 251 over 478 gives me 0.525, so 52.5%. That's called a marginal probability because we're using those marginal values I was telling you about. Now, sometimes we need to find a joint probability. So joint means we're talking about the inside part of this table. So let's say I want the probability of randomly selecting out of this pool of participants a woman who chose a camera. So I need the intersection of that row and column. So the probability of a woman is this row. The probability that our participant selected a camera is this column. So the probability of selecting a woman who also chose a camera is 91, that intersection. It's where those two values joint probabilities, they join up at that intersection. So 91 out of the total of possible people that we had participate, 478. So 0.190 would be their probability for that outcome. So contingency tables help us organize things a lot, and it also helps us to eliminate the number of times that we have to use a formula. So we could find these probabilities based on formulas, but that doesn't have to be the way that it happens. There's one more type of probability that we can find using a contingency table, and it's called a conditional probability. So in a conditional probability, we don't use the total for the whole promotion. We're going to use either a row total or a column total. So let's look at an example of that. So what if we want to find a conditional probability? And in a condition, we want to find a probability of an outcome given we already know that it's been narrowed down by some other variable. So what if we want to find the probability that somebody selected a bike, given we already know that that participant was a woman? So I already know that it's a woman. I don't need the total or the man row. I only need to look at the women's row. We know that it's a woman. We want the probability that she selected a bike. So the women that selected bikes was 30. The total number of women was 251. So that would be the ratio that I would use to find that probability. Now, let's say I don't have a contingency table and I need an equation for conditional probability if I just have those values and not a table where I can find those intersections so nicely. So here's another formula for us. If we want the probability, a conditional probability, so let's say the probability that B happens, given we already know that A happens, we would have the probability of A and B happening divided by the probability of A. So basically it's the same thing that we did in that table. We're looking at the probability of the intersection over the probability of it being a woman in that case. So it's the same thing, but this is in formula form and this is in contingency table form. Okay. And that little vertical line just means given. So the probability that B happens given the probability that A happens, or given the probability of A has already happened. So I think that's a pretty good place to start. I have lots of practice for these. So I will post that shortly. That way you can go ahead and do it now if you have time, since while it's fresh. But I will post this recording along with some practice, and that'll take care of our probability chapter. We'll add a little bit to it maybe, but not a lot. And then we need to add on one more topic before we can end the semester. Do we have any questions before we leave today? Well, if you need anything, you can type it in the chat box. If you have questions on anything, you can send me an email. Don't forget, everything has to be finished by June the 1st.